Hello Cyber Explorers, this is XK and welcome to CyberExplore. In this video, I will walk you through an important concept of theoretical computer science known as the Pigeonhole principle. First, I will explain the theory and then I will demonstrate two different applications of it. Well, there are lots of applications though, but for the sake of the length of this video, I chose the ones that are related to the topics that will be discussed in this channel sometime in near future. So, let's get started. What is a pigeonhole? Just a tiny house for a pigeon, although in this picture it looks more like a dog house from Tom and Jerry. But anyhow, in the backdrop of the concept, the actual shape and size doesn't matter. So let's assume we have n such empty houses and m homeless pigeons subjected to the constraint that m strictly greater than n, with the given objective that says none of the pigeons should be left homeless. In other words, accommodate all the pigeons. In this situation, we can use one of the following approaches. In the first approach, we follow the sequential allocation. That is, we fill the empty houses one by one, taking one pigeon at a time, till all the houses are filled, as you can see in the picture. Now recall that we have more pigeons than the number of houses, so we randomly assign the remaining pigeons like this. Fine, there goes the first approach. Now in the second approach, we simply assign them randomly and we get something like this. As a consequence, some of the houses might remain unoccupied at the end, but that's totally fine with the given objective, which only mentioned about accommodating all the pigeons and nothing related to occupying all the houses. But no matter whichever approach we follow, the pigeonhole principle still holds, which says that there will be at least one house with more than one pigeons, which is clear from the pictures. See? In mathematical terms, for m pigeons and n houses, if m minus n greater than equals 1, there will be at least one overlap if the given objective is to be completed. To make the understanding more concrete, let's apply in two different areas of computer science. Here I choose to explore data compression and hashing. Let's go with compression first. I guess you all know what a compression function is, but in case you don't know, a compression function encodes your original data or file into another form such that the size of the encoded data on the disk is less than the original data or file. The opposite to this operation is called decompression. It is simply decoding the compressed data or file into the original one that is usable once again. Now there is a popular question that says, can we have a single universal compression function that can compress every possible file? The answer depends on the context. Speaking literally, yes, but there is a caveat. It is only fine if you do not wish to get back the actual file each time. But that is synonymous to destroying the file itself, right? So not that convincing. But what if I add the statement that says all the original files must be uniquely recoverable from the compressed one? To answer this, let's turn back to the pigeons once again. Say the original file is n bits. Assume such a function exists. That means, according to the definition of compression, it must compress the file by at least 1 bit, right? So the file size must be at most n-1 bits. Now from the concept of binary digits, we know that the total number of possible unique n-bit files is 2 power n. So here the maximum number of original files or pigeon is 2 power n. Similarly, the number of compressed files or houses are 2 power n-1. So you see, we have more pigeons than the number of houses. So according to the pigeonhole principle, there will be at least one compressed file that will result in two different original or uncompressed files upon decompression. Also, if we calculate the average number of pigeons per house, we get 2 power n divided by 2 power n minus 1, which is 2. This means on an average for each house or compressed file, there will be 2 pigeons or original file. So we cannot recover uniquely, which contradicts the requirement of the given question. So the answer to the question is no. No universal compression function exists that can compress and uniquely decompress every file. Moving on to the next problem of hash collision. In case you don't know what a hash is, it is a fixed length textual signature of a text, file, or any kind of input. The algorithm that generates these hash signatures are called hash algorithms. So basically, they can encode anything to a constant length output text or hash, which is always the same for a particular text. The length of a hash is fixed for a particular algorithm. Now the question is, can hashes uniquely identify any data? Let's find out using the pigeonhole principle. We know the number of strings file input possible is infinite. So we have infinite number of pigeons to fit. And the number of hashes possible for an n-bit hash function has to be 2 power n, which means we only have 2 power n houses. Now since infinity is much greater than 2 power n, there will be at least one hash that will be generated from at least 2 different strings. So they cannot be unique. This phenomena in which 2 or more different strings results in the same hash is called hash collision. Also, if we calculate the number of pigeons per house, that is infinity divided by 2 power n, it results in infinity. This means on an average, there are infinitely many strings resulting in the same hash, or there exists infinitely many hash collisions per hash. As a result of this, hash acts like a one-way journey like time, which means from any string we can generate a hash, but from the hash we cannot trace back the one out of infinitely many strings that generated it in the first place. So theoretically it is not invertible, and due to this reason hashes are so useful in security. Instead of storing passwords, we store hashes of those passwords in online databases. If you want to know how to generate a hash, check out my previous video. The link must pop up somewhere around the top right corner. Anyhow, during authentication, the password that we enter is converted to its hash and matched against the hash value already stored in the database. The same password generates the same hash, so it can be verified. However, if an attacker steals the database, they cannot retrieve the original password from the hash as it is not invertible. Or can they? Well, the quest for knowledge will continue in another video in the future. Also, in the future, I will revisit this video when I will be discussing more about hash functions and hash collisions in more details. Going back to the original question, can hashes uniquely identify any data? The answer is no. To summarize, in this video, we learned about the pigeonhole principle and then went through two of its many applications. We learned a little bit about compression function and some concepts related to hash function. And that's all for this video. Thank you for watching. If you enjoyed it, please hit the thumbs up button and share it with someone who you think might enjoy as well. I will upload more videos on topics related to cybersecurity and programming on Python on this channel. Also, I'll be making videos on summarizing important case studies, research papers, vulnerabilities, and many more fascinating topics that you probably won't find in textbooks. So please hit the subscribe button if you want to learn more about the complex topics in security in simple terms. By the way, If you want me to make a video on a particular topic or paper in security, please mention it in the comments below. I will see you soon. Until then, stay safe and stay curious.